Our next speaker is Ants, going to tell us about waiting for commit. Thank you.
Okay, thank you. So, hopefully it's not too existential, but hello everybody. I'm Aasma. I'm going to be talking to you about this synchronous commit thing. I'm a lead database consultant at Cybertech, so we help people with Postgres issues, like Dmitry yesterday was talking to some of you about the synchronous replication detective story. That's the type of thing that we work on at Cybertech. So this talk is inspired about the same event, but I'm going to be slightly more general about this stuff. So I'm going to be talking about why do we need synchronous replication, how does it work, and so on. So why do we even need to replicate stuff? If there's anything constant in the world, is that things fail. Hardware fails, and last I checked, storage is also hardware, so storage will fail. And we still want to have our data even if our storage fails. So we have more than one copy of our data in more than one storage device, and we hope that they don't fail at the same time. And of course there is RAID that sometimes people use, which is also a form of replication. But in that case, we will have like either the storage area network or the RAID host bus adapter or anything like that. That will be a single point of failure for us. So we might still want to be able to have multiple different storage devices to have some diversity in case things fail. Another point of view to this is that durability and consistency that we talk about in ACID, they are like basically two sides of the same coin. They are both concerned, is my transaction still there? If I inserted something and I go back and check, do I see the result? And with consistency, it means that if we go to a replica, do I see our result? And with durability is, if there is a failure and we recover from the failure, is my data still there? So it's kind of a similar topic. And if you start thinking about things that might go wrong, there are some things that happen more often, some things that happen less often. And how much data can we lose in some cases, and maybe we don't care about their less probable things as much. So we might not want to protect ourselves against an asteroid impact, but if our operating system crashes, we better not lose any business transactions from that. So yeah, a recent event where people were not ready to have a backup ready, but in our case, we should always consider how much data are we willing to lose in case something happens. And because nobody likes losing data, they typically say we don't want to lose anything, and that's where synchronous replication comes in. So synchronous replication is all about waiting. It's not about doing something extra, it's delaying doing something until the time's right. So we need to figure out that this data is confirmed in enough different places that data loss cannot happen, at least for some value of cannot happen. There's always going to be some surprises. Then that's why we have backups. But the nice part of that is that there is almost no extra work needed for that. We just have to wait around and things magically happen. But waiting does mean that we have to, our things take longer because there is some extra time associated with it. And that also means that if you want to push the same number of things through the system per unit of time, we need to have more things in flight at the same time. So we need more connections, we need more memory for those connections, and so on. So it's not completely free, but at least we should be able to push similar amounts of things through the system. But to understand how it can go wrong, we first have to understand how it can go right. So let's figure out how synchronous replication works in Postgres. So first, a bit basics, just so everybody is on the same page. Postgres does all of its data changes in the write-ahead log. And the reason for that is if we need to make something durable, it's so much simpler to write everything into one place than it is to make sure that it's written correctly into a dozen different places. So write-ahead log is that one place where we log all our changes, and later we can do those 12 different places at our own leisure. And the other important part of that write-ahead log is that it encodes dependencies between those previous records and the next ones. And those dependencies can be logical, so if somebody draws out money from an ATM, that money better be deposited into their account before that. So that's a logical dependency on the transactions. But in Postgres write-ahead log, there are also physical dependencies, because we will have index structure changes, and if you have an index pointer that points to an empty space, the database might even crash. So it's really important that we cannot skip anything in the write-ahead log. We have to apply everything in order. So now that we have this discussed, this is how the write-ahead log will go through the system. So when the application finishes its transaction, it tells the database, make this durable, commit. That goes to your connection backend. It will create the transaction log record for the commit event, and that will get flashed to disk. And once it is durable on the local disk, only then we will poke the replication connections. Now, hey, there is some new transaction log, we need it replicated. And then our connection will wait for notification that everything is secure. Then at some point, the wall sender will wake up, see, okay, we have some data, it will read it, send it out over the network. It hopefully makes its way across to the replica side, and there's a wall receiver over there that gets notified there is new data coming in from the network. It will write it to the operating system cache, send back a notification that we have received the data. It will then flush it to disk, send back another notification that, okay, that data is now received and it's on our local disk durably. And it will then poke the startup process that will redo those changes on the replica side. And once that's done, there is another notification that the data has been also applied. Those notifications make their way back to the primary side, and then the wall sender can look at, is anybody waiting for this confirmation? And if they are, they get notified, okay, it's now durable on the replica side. And then the backend can finish its commit and tell the client, okay, the data is now durable. But while all of this is going on, the client does not know, is it committed or is it failed? So if something terrible happens during this process, they have to actually go back and check, was there an error or no? That comes back to bite us a bit later. So there's a ton of stuff that is going on here. So how long do those steps take? Can vary quite a lot depending on where are you running your databases. If you have your nice bare metal local NVMe disks, it might take something like 15 microseconds to 250. So a fraction of a millisecond. On network storage, it's more like half to 1 millisecond, more typical times. And if you have a network, the network can be to your next rack that is 1 meter away. That might be a couple hundred microseconds, but it might also be a different country, in which case we are talking about tens of milliseconds even. So it can be very different depending on what the scenario is. But just to understand what the numbers might end up, the very happy path, everything is bare metal, everything is working nicely, nothing goes wrong, we can expect that our synchronous commit will be like 0.3 of a millisecond. But if you are running on cloud, we want to do it across availability zones because US East 1 always goes down, then it might take a couple of milliseconds. So there is an almost order of magnitude difference between those two cases. But that's still like only a couple of milliseconds. That's always fine, right? Nobody cares about a couple of milliseconds. But there are a few reasons why it does matter. One of those cases is if you have lots of locking going on in the database. That extra few milliseconds, they are also added to the lock hold times. So anybody else who wants that lock will have to wait for that to happen. And the other thing is that we also need to have the connections available for those waits. So every millisecond extra latency means that we need one more connection for every 1,000 transactions per second that we want to push through it. And all of this is for the happy case. But things not always go as we want, and there are some things that might go wrong. So some examples that might happen with your commit is that we want to commit, but Postgres can right now only commit one transaction at a time, or there is one write to the write-ahead log at once. So if there is already somebody doing that, we have to wait for them to finish first, and only then we can start our own flush. Similarly, once our flush is done, we have to get the wall sender to send it out. But if it's scheduled on a CPU that is doing something else interesting at that moment, there might be up to a millisecond until we actually get woken up and start to send it out. And maybe that somebody else was generating a 10 megabyte bunch of write-ahead log for an index build or something other, and that might take tens of milliseconds to send out. And then when we finally send it out, the packet might get lost. So there are some numbers that on bigger networks, there is going to be expected like 0.1% of a packet loss always. And if the packet gets lost, we have to wait for like three other packets to arrive before retransmission is triggered, and we can get our write-ahead log across. Also on the receiving side, we might be busy, so that's another place where we can get delayed. And we might be doing something else on the receiving side, so we are still processing the previous commit. That's another delay. And when we send the data back, we can again hit packet loss, we can again have some delays before it's noticed, and so on and so forth. And those are just the normal stuff that happens every day. You are expected to happen multiple times a second. But there is also the stuff that goes more wrong. So if you might have your like multipath driver get confused for 20-second delay, your storage fabric does a denial of service to itself, 60 seconds delay to some IOs, or the standby dies. What do you do then? Do you disable synchronous replication? When do you notice that? And so on. So those delays might be quite long in that case. So something that can help with that is configuring your synchronization to different levels. So you can do that in Postgres for every transaction. You can pick your synchronization level that you expect. So you might have some stuff that you don't care at all about, or you care very little about. So for those ones, you can turn synchronous commit off, and hopefully it will make it to disk at some point in time, but you don't really get very annoyed if it doesn't. But for other ones, you might want to have the remote write or on options, which make sure that it is present on the replica, so we can survive a failover. These days we are almost always running high availability systems, and we care even less about is it on the primary, because if the primary dies, we don't want to wait for it to recover. We actually want to fail over quickly to get the system back up and running, and we care even more that it's present on the replica. But is it on the disk on replica or not? That's not as important, because we might not expect both of them to die at the same time. So a remote write could be good enough. And there's also this remote apply, so if we want to read from the replica and see our result, that is what gets us read after write consistency. But with remote apply, there are even more things that can cause waits. So use that very cautiously. And the reason is that there is head-of-line blocking. So if one commit is blocked, everything that comes after it also needs to be blocked because, as I said, the write-ahead log is encoding dependencies. We cannot skip a part of it. We have to do everything in order. And if a replica is busy syncing to disk, it cannot confirm transactions. So that means remote write actually doesn't help us that much these days, at least when it comes to syncing to disk on the replica. And you can also get some consistency issues with this because when you issue the commit and it hangs because of whatever is going wrong on the standby, if you are doing it interactively, you can hit Ctrl+C, but the application can do a similar thing, or the connection might be dropped. And if you are writing a reliable application, you write the application in a way where you take some data that you need to store, and you try to store it. If you get an error, you retry. And once you get the confirmation back, then you can release the data, and you know that the database has it. But the trouble is that if you fail during the commit, you cannot know did it succeed or not, so you go and read. You see, the thing that I inserted is still there, so I can ignore it. But the trouble is that Postgres has a thing where if you cancel, wait for the synchronous replication, the commit becomes immediately visible, even if it's not replicated yet to the replica. So if there is now a failover, that data that you just happily confirmed that it is present on the primary is no longer there on the replica after this failover. And it might seem like very improbable to have all of those things happen at the same time, but typically those things are caused by the same symptoms. So you might have some network failure going on, which causes the replication to break, which causes the synchronous commit to wait, and then you need to do a failover for that. So they are not independent events in that sense, so you have to actually care about this. So you have to be very careful about such retry loops. So even if you have this synchronous commit on, you have to actually, when you're rechecking, did I insert it or not, the way to handle it is you push another commit through. You select txid current, for example, that will create the writing transaction. And if you are successfully have committed that, you know that the previous data that I looked at is also there. But how do we see those performance issues in synchronous replication? You can actually use pgstat statements to see how much time are your commits taking. But this will give you the average. The slightly better solution is to track wait events. There's going to be a few related to this durability stuff. The main one is I/O wall sync. That's when we are doing the local disk write. Then there's going to be LW lock wall write. So this is before we even get to the wall sync. We have to wait for everybody else to finish before us. So that's basically the same thing, but we are just in the queue to do the next wall sync. And finally, we have this IPC sync rep wait event, which means that we are waiting for confirmation from standby. And we can look at those events in pgstat activity, and that might indicate some problems to us already. But if you want to get the high resolution detailed statistics, pg-weight sampling can help you get those slightly better information. But from that, we only know that we are waiting for synchronous replication. We have no idea why is the synchronous replication slow. So there are some options to get better information, but not in Postgres, unfortunately. So we can use system tools like strace or perf to record what syscalls are happening and reverse engineer from that what is actually slow. And for that, I built a small tool to analyze the perf output to find what are the outliers. So you can run this perf record command on your wall receiver, and then you will get out of that this kind of a latency table, for example, that we can say that if data sync took more than 10 milliseconds in 16 cases. And you can even list all of those cases to see were they correlated in time, did they happen randomly, what was going on. And when you're looking at those, write this, when we write to the operating system cache, if data sync is, we flush it to disk, equal wait is, we are waiting for stuff on the network, and if sync is done when we are switching writer log files. So what can we do about the problem? Well, typically we can throw hardware at the issue. We can buy a better storage device, maybe, or we can buy more IOPS from our cloud vendor, because when the systems are not as highly overloaded, when they have low loads, it's less likely to hit like those tail latency issues that we might see. But another good option is to use quorum commit to hide tail latencies. So we can add more replicas, and hopefully at least one of them is working quickly. So we need at least 2 replicas for that to make any sense. And how this quorum commit works is that we specify in our synchronous standby names that we are happy if any one of those nodes has our commit durable. But the primary still needs to flush, so if there is any slowness in the primary, we are still slow anyway. So we could improve Postgres in this area to make Postgres able to do quorum commit across the primary and all replicas simultaneously. So we don't have to wait for the local flush before we replicate. But the tricky part here is when the primary now fails, we need to pick the correct replica to promote, otherwise we still lose data. And the way to do it is, if we are happy if one of them confirms, we have to look at every one of them to find that one. If we wait for a response from 2 of them, we can also have one of them missing. And we have to look at both the last wall receiving location and the last replay location, because in some cases one of them is missing, the other one is missing. So pick the highest value of those 2 and pick the replica with the highest value in total, and that one is the one that you need to promote. That's a bit tricky to automate, so my recommendation is use Patroni. Patroni synchronous mode quorum just makes it work out of the box. So, in summary, figure out if you can lose transactions. If you cannot, just know that every performance issue you might have in your system is greatly amplified by synchronous replication. And be prepared to have more connections and add replicas to hide your latencies. And if you need to do quorum commit, use existing tools. But that's it. Thank you.
Any questions? He's coming over there with the mic.
If you notice sync rep wait event on the primary database, what's your troubleshooting workflow to find the root cause? What caused those latencies?
I would just go to the tracing.
Based on wait events, do you have anything to suggest? If you have only wait events.
But if you have only wait events, yeah, there is nothing today in Postgres. I have some ideas what we could add, but right now it's not there.
No? Any? Oh.
Hello. I have a question about the tool that you demonstrated, the perf tool.
Yeah.
You, as far as I can see it, you use it outside of the Postgres environment. Is that right?
Yes. It runs outside of Postgres. You can trace the whole system. You can trace some Postgres processes. If you can give it some process ID and you can monitor either all of the syscalls, or you can go even more low level and you can see like block requests to actual block devices.
It uses the Unix process IDs and
yes.
The Postgres.
But those are visible in the process speech stat activity. So.
Okay, but you have to go into. You have to go into Postgres then.
Yes.
Anybody else? Thank you, Ants.